Good morning and welcome to the seminar of the Astronomical Institute of Charles University. Today we've had some technical troubles, so I will not delay the talk by any complicated introduction. I will just say that today's speaker is Pavel Kroupa, who is a member of our staff, but who is also a member of the staff at the University of Bonn in Germany. And I think that he's been a member of staffs all over the globe throughout his whole scientific career, where he was basically doing almost every topic in astronomy and astrophysics. And today he will give us a talk about the origin of brown dwarfs. So please, Pavel, can you start?
Yes, I hope I can be heard by everybody.
Yes.
Yeah, good.
Yes.
And the slide is visible and the cursor also, right?
Yes.
So it's a pleasure to be presenting this topic, which is a topic which I've been working on quite a lot in the past with important collaborators. And so let me begin. So when we look at a galaxy, we know today that the vast majority of galaxies, essentially nearly every galaxy out there, is forming stars. And so in order to understand these galaxies, we of course need to understand how these stars form. So essentially it's the problem of how the interstellar medium or the gaseous atmosphere of the galaxy converts into ballistic particles, which are the stars, which then decouple from the gas and become a purely dynamical, ballistic components which contribute to shaping the galaxies. And so this process of conversion of gas to stars is very much at the core of modern astrophysics, in cosmology, in understanding how galaxies evolve, and also, of course, for the star formation process itself. And so what rules do this process of transforming the gas into stars obey? And that's basically the topic. So when we look at the regions of star formation, like here, they look complicated. So here is a young cluster which formed, and there seem to be some sort of subclusters here, and then there's an older cluster up here. And overall, it seems simply complicated. So we do know from observations of molecular clouds of embedded, of the sites where stars are forming, that they form in embedded clusters. Here we have a particularly nice example, the Orion Nebula cluster, which is at half a kiloparsec from us, is the nearest object forming ionizing stars, plus thousands of low mass stars. And then we also have an object like this one, which is the Pleiades cluster, which is about 100 million years old. So this is 1 million years old roughly, and this is 100 million years old. And so clusters are very good places to look at, to understand, to try to extract the rules, which, if there are any rules, which this process of converting gas into stars obeys. So we know that the outcome of star formation are stars and also brown dwarfs. Yeah, that's observationally understood. So stars, as everybody will know, are sufficiently massive to power nuclear fusion. Brown dwarfs are not massive enough to power nuclear fusion. They've been discovered by Rebolo et al. In the Canary Islands at the IAC in 1995. Prior to that, brown dwarfs were hypothetical objects. There was a decades-long discussion about whether they exist. And then they were actually discovered, and today hundreds of them are known. And the boundary between stars and brown dwarfs is at approximately 0.08 solar masses. So objects below 0.08 solar masses are in this category, and above that they are sufficiently massive to power nuclear fusions in their centers, which then keeps the star going. And so here is an example from a previous work. You see, this is before they were actually discovered. So Adam Burrows did some very seminal work on this. We have here the radius of the gas cloud as it's collapsing. And this is at a very late stage when there's already a hydrostatic object which formed, which is opaque. So it stopped contracting. It's contracting slowly in this calculation. And this is the time. So here we have 1 billion years, and this is 10 million years over here. And so the radius decreases, as you can see. In fact, there's a flattening up there, which comes from a certain. So the gas cloud core collapses, forms a hydrostatic core when the opacity becomes large, because then it can't collapse further. It has to wait until it cools off. And as it shrinks, it actually follows from up here down there. And then at some point, it stops contracting because deuterium burning stabilizes the structure. And that's what you see with these steps here. These ones also have these steps, but they are off the graph. And then when the deuterium is used up, it starts to contract. And so we see the later stages of the contraction. This here you can see is a 0.2 solar mass object, and it stabilizes here through nuclear fusion. And that's when it becomes part of the main sequence at a time of about 100 million years. It reaches the main sequence. And as we go to lower mass, so this is 0.01, this is 0.0110, and so on. So as we go to lower mass, the same happens. So we can see here these are the stars, but then these types of objects, they just contract. Again, some of them are stabilized by deuterium burning slightly. You can see this one too, and then they finally just stop contracting, but in this case not because of nuclear fusion, but because electron degeneracy stops further contraction. So they attain a fixed radius for aeons, many Hubble times, if one would just continue here, and they just cool. And that's how they crystallize ultimately, or whatever happens to them. Now, this is what happens with the luminosity. So here we now have the luminosity in units of solar luminosity. And this object here, 0.2 solar masses, this one here, you see is here stabilized through deuterium burning. Once deuterium is used up, it contracts. The luminosity decreases because the radius decreases. And the temperature more or less remains about the same, but since the radius decreases, luminosity decreases, and then it stabilizes here at 100 million years on the main sequence and just goes on and on for a few Hubble times. And these ones down here, they just keep cooling. The luminosity decreases, although the radius is constant. Here on the left, you can see that they just lose luminosity as they cool and cool further to oblivion. And so we can see this separation here between stars and brown dwarfs. That's the technical the definition of these objects here. This would be a brown dwarf, and this is still a star. Yeah. And so the issue is brown dwarfs have been now discovered. Fundamentally, star formation should produce stars and brown dwarfs. Why should there be any difference in the rules they obey, or are there any rules at all? Here's another more recent calculation from these people here, where one can see again the stellar radius versus a stellar mass in this case here. So we see here one solar mass would be one solar radius. And the dashed line is at 400 million years. The solid line is at 5 billion years. So one calculates these objects up until 5 billion years. And these are observed low mass stars. And you can see that the theoretical models, the models actually quite nicely reproduce these observed stars, and only at the lowest masses do we see that the cooling continues, and the settling of the final settling to a smaller radius, which then stabilizes at about this point at this radius for these very low mass brown dwarfs. So that's, you can see here the nice distinction between stars on the right and brown dwarfs on the left. With this minimum radius, and then they get a little bit bigger, and this is an observed brown dwarfs at that time. And so below about 0.08 solar masses, further contraction stopped due to electron degeneracy pressure. And here's now what we see in a star forming region. It looks very complicated. What happened here is that an embedded cluster formed. The most massive star, which is an ionizing star, started ionizing the nebula. This object is about 1 million years old. It's the star forming region S106. And the ionizing star blew out along the polar regions the material, so the H2 region is breaking out. It's opened up partially to us, towards the observers, so hot gas is now moving out towards us, and also impinging on the rest of the molecular cloud here. This is a very dynamic picture. If you look at probably 1,000 years later, this would already look very different. And we can still see the remnants of the actually rotating structure which formed the embedded clusters. So this would imply, I would imagine, this is now just speculation, that embedded clusters must form rotating. Yeah? And then there's a polar region where the H2 region first breaks out until the entire molecular cloud in the inner region here is destroyed. Anyway, it looks complicated. So it's, the star formation process appears to be messy and very complicated, and it is easy then to argue that star formation is stochastic, because that's what it sort of looks like. Yeah, it looks messy and stochastic. The challenge, the art of the game, is to actually find patterns and rules, which they might be in the data, but of course one needs to spend time and thinking on trying to extract these rules. And so one such effort is to constrain the shape of the initial distribution function of stellar masses, the IMF, the initial mass function. And related to this issue of the star formation being purely stochastic, so anything happens anywhere, essentially, more or less, versus a star formation obeying clear patterns and rules, is this question whether the IMF is a probability density distribution function. So can one just take stars from the distribution function randomly, or is the IMF the exactly opposite? So is it an optimally sampled distribution function where one does not take stars randomly, but according to a very, very specified sequence, which depends on the boundary conditions? So the IMF is shown here. It's the distribution of stellar masses bound together. That together means within about a crossing time of the embedded cluster, so within a time span of some few hundred million years, a few 100,000 years, less than a million years. This is how it's written. So this here is the n is the number of stars in this mass interval here, and the shape today is understood to be this form. This is the salpeter Paulo above about 0.5 solar masses here. They are the ionizing stars, which are very rare, and then we have a flattening of the slope value of about 1.3. So this is a slope of 2.3. This alpha is 2.3. Then this here is about 1.3. And then we have the brown dwarfs at this end. So this is about the hydrogen burning mass limit here. And the question is, how do the brown dwarfs fit into this mass distribution? Is the mass distribution just a continuum somehow, continuous, or does it actually cut off here in the stellar regime? And are the brown dwarfs largely a separate population which we have to add onto the stars? And this is something which we want to investigate. So the IMF has been measured. For example, here's a fairly recent survey by Musitz et al. In RCW38. This is a deeply embedded, young, 1 million year old massive star cluster located at this 1.7 kiloparsec. It has an incredible density. This is a much denser cluster than the Orion Nebula cluster. And that's what it looks like. So that's the whole region. You see this, the scale of 5 parsecs on the sky. That's what has been so far found and observed. Each point is a star, and these people have surveyed this very most inner region, which is less than a parsec across. And this very dense inner region is equivalent to the trapezium region, the Orion Nebula cluster, except this is denser. So the whole cluster is actually much more massive. That's what they've surveyed, and they found that. So before I come to what they found, we have to realize that such clusters. So we see the snapshot and it looks static, because if you take a picture of this 10 years later, not much has changed, except maybe some of the gas features might have slightly changed. However, from stellar dynamical simulations, we know that these objects are very compact. So this is a movie of a star cluster which is equivalently dense, very compact. And look what happens. Up here, you've got the time. What in here, you see the initial configuration is very complex, less than a parsec in radius. You see the scale here is 100 parsecs across 100 parsecs. The most massive stars are blue. The 1 solar mass stars are red, and this calculation includes all the stars below 1 solar mass, but they are not shown because there are just too many. And see, within a fraction of a million years, the star cluster already expels massive stars with high velocities, intermediate mass stars. And look at this. This is a binary which was expelled, which then merges to become a more massive star. You see now it's merged, so this is like a blue straggler now, but it's moving away from the cluster. So an observer trying to infer if this fits to that cluster would say it doesn't, because it looks too young compared to this cluster. So within a few million years, one or few million years, the cluster's already spread its stars to regions of 100 parsecs around itself. Yeah? So despite starting extremely compact. And so these things are very dynamically compact. That's something one has to take into account in trying to understand these observations. So what one does know from these star counts for observations is brown dwarfs are very common. And here, this is now what the Musitz team has found. This is the number of stars versus mass. You see here is 10 solar masses, and here is 0.1. And so the brown dwarf regime boundary is here, and they've discovered a lot of brown dwarf candidates up here. So the mass distribution they discovered from a Monte Carlo experiment, so they have an observed data point with uncertainties, and within these uncertainties, the sample given an isochrone to infer the possible masses which go into that one point, and that's why one has the spread. And so the overall shape of the mass distribution is very comparable to the canonical IMF, which with a salpeter slope here and the flattening, you see again at about 0.5 solar masses, the data do indicate this flattening. And then they found many brown dwarfs. In fact, in all regions studied so far, citing from their paper, we find that the star to brown dwarf ratio is between 2 and 5. So something like 10 low mass stars. So when 10 low mass stars form, in addition to that, 2 to 5 brown dwarfs are also forming. Okay, and this is what we also infer from the field. I'll come to that a bit later. And this is another survey by the same team here in the Chameleon 1 and Eta Carina chameleon star forming region. Again, they find basically the same result. Again, you can see here, this is the brown dwarf boundary. These are stars, and here would be brown dwarfs. And it appears that there's a continuation into the brown dwarf regime without any break, as if stars form just like stars, and there's no difference. But it is a problem to form only a brown dwarf. So these observations suggest that brown dwarfs are very common, just like stars. But if you think about the theoretical aspects, to form a brown dwarf is actually very hard, because what you need is a molecular cloud core which actually would then collapse and has a total mass which is below this boundary and is gravitationally unstable, which means it has to be very dense in order to collapse at that low mass. Furthermore, it must not accrete further material from the surroundings to go beyond this limit, right? And these conditions make the formation of brown dwarfs extremely difficult, very, very rare. In fact, we've looked at this with Ingutis et al. Here, and in that paper we write that the fundamental reason why direct fragmentation of a turbulent molecular cloud rarely produces brown dwarfs is that the formation of a brown dwarf requires a high-density, gravitationally self-bound but very low mass fluctuation that cannot draw significant amounts of additional mass from an accretion reservoir. So therefore, observing many brown dwarfs is actually in conflict with what we know about star formation, just from direct collapse of molecular cloud cores. And it is exceedingly rare to obtain density fluctuations in molecular clouds to make a solitary brown dwarf. So how is it possible that one observes so many brown dwarfs if we have this obstacle? And that's a fundamental obstacle. This is not something we can get rid of with some uncertainties in theory. Brown dwarfs should truly be rare, but they seem to be very common. And so the observed IMF contains too many brown dwarfs compared to the IMF predicted from graviturbulent theory. So we looked here in this paper at what these people predicted from this theory. So they model the molecular cloud as a turbulent field, which has these density spikes in it from the shocks, and they assume that these form stars or brown dwarfs, and then they predict that from this theory that one has a certain shape of the mass function, and this goes into the brown dwarf regime. So this is what they predict. This is now the Padoan-Nordlund case, a cloud with a Mach 10 velocity field in it, and this is what the theory predicts, or gives at least, of course, after some adjustments to agree here with the salpeter slope. And this is the number of brown dwarfs. You see, this is the mass, 0.1 solar masses here. This is 1 solar mass. So they predict this number of brown dwarfs from this theory. What is observed is this red curve here. That's from observations, essentially, as we've discussed this paper. And so there's a surplus of brown dwarfs, which is very substantial at these very low masses, where the theory cannot account for the observed brown dwarfs. And this, what is being plotted here, is the system IMF, i.e. the fact that the stars actually come in binaries. And we now come to binaries, which are a very important aspect of this whole problem. So to better understand the data, we need to first digress to the systematic bias through unresolved binary systems. So it's not just an issue of counting your unresolved stars in the system. One has to understand how these are actually distributed into binary systems and how the binary systems evolve in these embedded clusters. So the problem becomes quite difficult and complicated. Here's just an example. Again, this is the mass function here against the mass. So this is 1 solar mass. This is 0.1 solar mass. So we are now here looking only at the stellar component, ignoring brown dwarfs. You can see that this is the two-part Paolo IMF here, the standard canonical IMF, from which one draws stars and then combines them into binaries according to the rules I'll briefly touch upon in a moment. And you can see that the observer would find this turnover in the system mass function, which is orders of magnitude, would give us orders of magnitude fewer stars than they actually are in the system, because these low mass stars are hidden as companions to the brighter systems. This comes about because the pairing rules change here for the massive stars. Here we have random pairing. So we actually do take stars randomly from the IMF to combine them into binaries, and that's a rule which works extremely well. And so this is a strong bias which the observer is subject to. So important is to model the effects of unresolved binaries. One must first make an array of the stellar masses from the IMF, then pair them. So it is wrong to take the IMF, take a primary, and then take a mass ratio distribution to give the primary secondary, because if one does that, one changes the IMF. If we do not want to change the IMF, which we're not allowed to because that's now constrained very well from observations, we have to first make an array of stars which we pick from the IMF, and then we only play with this array of stars so that the actual IMF is not changed. Okay, so first taking primaries from the IMF and then secondaries from the mass ratio distribution changes the IMF. Now, most people in the community make this error, which is a great shame, but this is often done, and that's just not correct. And so just coming back to the, just to show the bias of the, from binaries, we have here the number of stars versus the mass again, as I've shown before. And we now look at this Paolo index here as a function of stellar mass. So for example, here we have two values. We have 2.3 as the salpeter value in this mass range here, and then we have 1.3 in this mass range below 0.5 solar masses. This, so we can plot alpha as a function of mass, here. So this is alpha as a function of mass. This is what I just said. This is the value of 2.3 above 0.5 solar masses. This is a value of 1.3 in the regime between 0.08 and 0.5 solar masses, and independent work has now indicated that the brown dwarfs have a slope of 0.3, so it's a nice sequence of numbers here. Now this is just a schematic, so what an observer would do, looks at one cluster, embedded cluster, and finds the IMF in this mass range, so this alpha in this mass range, the alpha in this mass range, and in this mass range, and that's what it then would look like. And the alpha in this mass range here, in this mass range, and that mass range. This dispersion is due to measurement uncertainties, but the mean typically gives the salpeter power law, and down here we would then get this 1.3. Now, this is what it looks like. So from such an analysis, one finds that a good working hypothesis for the star forming around us, around the sun, within the Milky Way disk, is that the IMF is quite universal. It doesn't actually change these alpha values significantly. And so the alpha plot looks as follows. This is now the actual real version. So this is again alpha value. This is the salpeter power slope, power law here. This is the value of 1.3. This here is 1 solar mass. This is 10 solar masses, you can see here. And here are the brown dwarfs in this regime. And we're not going to discuss the massive stars, which are also interesting, but here only the low mass stars. So we see that the power law changes. These are actual systems observed, like the Pleiades, the Orion Nebula cluster. We have globular clusters, young clusters in the Milky Way, young clusters in the Large Magellanic Cloud. The triangles are all Magellanic Cloud. And so you can see that these data are clustering very nicely at this value of 2.3. And at this lower mass value between the hydrogen burning mass limit and the value of 0.5 solar masses, the observed values all cluster at a value which is below the 1.3 here, you see. So the observer would first think that the mass function is shallower than the value of 1.3, but this is because of unresolved multiple systems, because if we actually start with this, put the stars in these surveys into binaries, according to a binary fraction of, say, 50%, which is what is typical for these systems, then the unresolved binaries or unresolved systems would actually look like a mass function of stars which has this slope down here. So this bias is very well understood and is very, very important. And for the brown dwarfs, you can see that the data scatter largely. The observations are much, much more difficult here. But overall, the mass functions flattens from this regime, from this value here of 1.3 to something like 0.3 in this regime. There's quite some uncertainty, but it's definitely flatter. At least the power law in this regime is flatter than that slope for the stars. Now, this doesn't mean that it's discontinuous. So we just have a power law which continues at the salpeter, then flattens in the stars, and then brown dwarfs, it flattens a little bit more, potentially. So the bias, so a very large bias due to unresolved binaries exists here. The observer will not see all the stars in the system because many of the faint stars are companions to the brighter stars, and the bias depends on the state of dynamical processing of the initial binary population. So this adds a degree of complication to the whole problem. So the binaries, we need to understand them. In order to understand brown dwarfs, how they form, and if they form like stars, given just the data, we first have to understand the brown dwarf the binary star problem. Okay, so to quantify the dynamical processing, we first need to seek the initial distribution functions of binary stars. To make statements about how the binary population evolves, we need initial distribution functions. So that's like the IMF. In order to model the galaxies or star classes, we need an IMF, which is a model for the distribution of stars as when they condense out of the interstellar medium together in one cluster. And the same thing, we now need a mathematical description of how to actually create these binary systems from the stellar systems, from the stars which form in this embedded cluster. And I've done a lot of research on this. So there are three distribution functions. There's the initial distribution function of periods or equivalently binding energies. That has to be inferred. Then there's the initial distribution function of mass ratios. That has to be inferred. And there's the initial distribution function of eccentricities, which also has to be inferred from the data. So you can see we have here three distribution functions. In addition to that, of course, we have the distribution function of initial masses, and that's the IMF. So we have these four distribution functions which define a stellar population we need to put into the computer if you want to make any simulations, which makes sense. Now, we know that the angular momentum in collapsing pre-stellar core is always large. So when we look at observations, we know that these pre-stellar cores, which haven't yet made a star, are rotating. And they have far too much angular momentum. And one way this structure can collapse to form a star is to break up into at least two stars, to make at least two stars. Okay, they must form a multiple system, at least, maybe 3 or 4 stars. And so what the observations tell us is as follows. So here we have the period of solar type binaries, and this is the frequency, how often they occur. So for example, if you look at the sky, at all stars which are one solar mass, then we see that about 8% of all the G stars we see on the sky, 8% of them are binaries with a companion which has a period of 10 to the 3, so about 3,000 days. Okay, while something like 10,000, 13 or 30,000 day periods are found for these G-dwarf binaries at 10%. So 10% of all G-dwarfs have a companion with an orbital period about the G-dwarf of with a period of about 30,000 or so days. And so the observations have shown us that this distribution of periods is a log normal in the field, And the area under this tells us that every second G dwarf on the sky is a binary, and the binaries are distributed according to this distribution of periods. But these are field stars. These are not the stars which actually we find in observation in star-forming regions. And that's what happens in star-forming regions. So each of these is now a particular region which has been surveyed. Like this is canonical pre-main sequence from many surveys here. And then here we have the lupus star-forming regions, are these squares. And all of them tell us that in star-forming regions, when the stars are still very, very young, they seem to be completely only in binaries. But later in the field, half of them are in binaries. So something happens along the way. And so that's the work I've done in the 1990s. I've inferred this distribution function, which is consistent with these data and evolves in star clusters. That's this omega operator here, omega dynamical operator here. So this distribution function evolves to this distribution function, but one has to go through these star clusters, embedded clusters, and then one can explain the field and one explains the star-forming region. So it's a unification, you could say, of these observations, but you need the stellar dynamics in a star cluster to do this. So the observed very high binary fraction in low density, 1 million year old star-forming regions implies that stars must very much preferentially form binaries, not triples and quadruples, because if they would form binaries and triples and quadruples, then these triples and quadruples, they decay within 10,000 to 100,000 years. Just the orbital, if you have a hierarchical triple system, it lives for something like 10,000 to 100,000 years and shoots out one star. They are dynamically unstable. The same with the quadruple. It lives for the crossing time of the system and then decays by shooting out one star and then shooting out another star, leaving a binary. But then, so within a short time, one would, if this were the case, observe a binary fraction in these 1 million year old regions, which is actually 50% or even only 30%, depending on triples or quadruples, if you just think about it. Yeah. And so since we observe a very high fraction of multiple systems at 1 million years old, it means that essentially only binaries form with a few triples and quadruples. And if triples and quadruples do form, then typically they must be hierarchical. So they must be stable and survive for 1 million years. So this already gives us strong constraints that the star formation process typically forms a binary rather than triple and quadruple. And so stars and brown dwarfs form in embedded clusters. This is observed. There are simulations which are very hard. So you can always do one simulation of a cluster with 100 stars, and that's it. It takes months. So one learns a lot, but one is not able to synthesize whole galaxies in this hydrodynamical simulations here. So the initial binary population is dynamically processed in these embedded clusters. And this is what we see here. So starting an embedded cluster, a young cluster with 100% binaries, the binary fraction decreases with time. And depending on the size of the cluster, the binary processing is minor, significant, or too much. So the binary fraction of the galactic field is in this at this level, which tells us that these clusters with a half mass radius of 0.8 parsecs, give us the right dynamics to evolve the initial distribution of 100%, as we observe in star-forming regions, into the galactic field population. So typically stars form in embedded clusters equivalent to an embedded cluster with this radius containing 200 binaries. If the cluster is too small, too many binaries are destroyed and we cannot explain the field. Okay, so this is a very interesting result. And if we start a star cluster without binaries, some binaries form through encounters, but the number is always far, far, far too small to explain the high fraction of binaries in the galactic field. Okay, so the observed distribution functions of stellar binaries in all observed populations, so their periods, mass ratios, and eccentricities, are today very well understood and in fact consistent with being universal, just like the IMF, in the star-forming regions around the sun. if their origin in embedded clusters is taken care of course. So you need to take into account this the dynamical processing. So this leads to the universality hypothesis. The binary and stellar populations in star clusters and galaxies are quite universal concerning star formation as we see it in our Milky Way galaxy today. And so we have a consistent description of the stellar binary population in star-forming regions and in the Milky Way field. And all stars form in binaries with well-defined birth period and birth eccentricity distribution. There's quite a lot of literature on this now. As long as the primaries have masses less than 5 solar mass, and companion masses are then taken randomly from the IMF. So if we have a primary less massive than 5 solar masses, its companions can be randomly chosen from the IMF. Above that, that is not the case. But so we have these rules for stars, which are really well understood, and we can synthesize the galactic field very, very nicely now. The problem is that brown dwarfs totally do not fit into these rules. And that's the interesting clue to the formation of brown dwarfs. So brown dwarfs and stellar binary systems. So the brown dwarf, there's what we refer to as the brown dwarf desert, or which other people have referred to as the brown dwarf desert. The number of star brown dwarf binaries is exceedingly rare. So while finding a star with a stellar companion is common, that's usually the case. When you look out in the sky, every second star has a companion, which is a star. Finding a star with a brown dwarf companion is extremely rare, less than 5%. So star-star binaries are common, and then if you look at those, if you do a survey of brown dwarfs, and if they have the brown dwarf binaries are themselves rare, so the brown dwarf binaries occur in about 15% of all brown dwarfs one looks at, while the star-star binaries are very common. About 55% of all the stars are binaries. So they don't mix, plus the brown dwarf binary fraction is much lower than the stellar binary fraction. This indicates that brown dwarfs do not form like stars, because if they would form like stars, they would follow the same rules like stars, but they obviously do not follow the same rules. They have their own rules, which we now have to try to uncover. So stars and brown dwarfs don't mix in the same sense of, I mean, they form together, but they don't mix in the sense of making bound pairs. So this is nicely shown in this survey by Lafreniere et al., where one sees here the mass ratio versus primary mass. So for example, a sun-like star has companions which go from this dashed line upwards. So it can have a companion which is, say, 0.1 solar mass, it can have 0.2, 0.3, up to 1 solar mass. A star, a 0.2 solar mass star would have a companion which is which is larger than a mass ratio of this value here. So it cannot have a companion in this regime because they are non-observed. We can model this just simply by reproducing the same diagram here and just taking the IMF and pairing randomly, but only in the regime 0.08 to 5 solar masses. Then we can nicely explain these observations. If we extend this pairing, random pairing boundary down to 0.01, we get this part of the distribution, which is inconsistent with the observed one. So we would expect, if this were the case, that 0.1 solar mass stars should have companions which go down to very low masses into the brown dwarf regime with a mass ratio of 0.1, so 1/100th of a mass, which is not what is observed, as you can see. There's nothing here. And so this clearly tells us that if we want to make binaries, synthesize binaries between brown dwarfs and stars, we have to make a distinction. We first treat the stars separately, and then we treat the brown dwarfs separately. That's the algorithmic description. Furthermore, the binding energy distributions are different. So this is the fraction of binaries on the left here, and that's the semi-major axis. So here's 10 astronomical units. This is 1 astronomical unit. This green and blue curve is what we see in the galactic field for G dwarfs and for M dwarfs. This is the log normal distribution I showed before. These observational data points here from Fisher and Marcy and so on. And we see that Stars have a very broad distribution of semi-major axes. Extends, you get stellar binaries with a separation up to 1,000, 10,000 AU, as well as very tight stellar binaries here. But the brown dwarfs, that's the brown dwarf distribution here, are very, very compact. So only a small fraction of brown dwarfs are binaries, but those which are binaries have semi-major axes, typically of 5 astronomical units with a very narrow range. So this tells us again that the brown dwarf binaries follow a different distribution function to that of stars. Okay, and so it's clear here from this survey that there are no additional significant brown dwarf binaries in this regime. So the star-star binaries are very common. Star-brown dwarf binaries are very rare. So brown dwarf binaries are very rare. And period distribution function of stars is broad, with a maximum around 30 AU. And the period distribution function of brown dwarfs is narrow. And so all of this indicates that stars and brown dwarfs do not mix, and actually they follow different distribution functions. Okay, so we cannot apply the stellar distribution functions to include brown dwarfs. I've tried it, but there is no room. You can't add brown dwarfs according to these rules into the distribution, because you would always be inconsistent with the observational data. So we need extra rules to include brown dwarfs into our populations and thesis. We need to mathematically teach brown dwarfs separately to stars. If you write a computer program which you want to include brown dwarfs, you need to have an if statement. If stellar mass, then you do your stellar population. If brown dwarf mass, then you do your brown dwarf population. You cannot put them together. So brown dwarfs as a separate population. Just like planets, brown dwarfs form with stars, but they follow their own rules. And so here is now, if you want to infer the mass function from an observed mass function, so here we have the mass, and this is the number density. Imagine that you observe just independent of mass, always the same number of objects. So the mass function is completely flat. If we now correct for unresolved binaries, for the fact that stars, every second star is a binary, then we add the corresponding number of stars into the system, and so the mass function ends up being up here, and then it stops because we're looking at stars. If you do the same thing in the brown dwarf regime, then we see that the correction for unresolved companions only ends up here, so we have a discontinuity in the mass function. This indicates that the mass function of stars ends, and the mass function of brown dwarfs is just a separate entity. And so this is what we've done. We've looked at the Pleiades and other systems, and we can see here the number versus mass. So this is 1 solar mass, this is 0.1 solar mass here. This is brown dwarfs, and these observational data here, as well as here for the high mass end here in the stellar regime. The canonical IMF in the stellar regime is this one here. That's the salpeter slope, and this is the slope of 1.3. And we make binary systems out of this, and that's the red curve for the Pleiades, which nicely matches the star counts in the system. And then we treat the brown dwarfs as a separate population with 15% binaries, and that altogether gives this red curve with this discontinuity because we have observational uncertainties, so any sharp cuts are smoothed out. And so the observer sees this red curve, which is nicely consistent with the observed data, in fact, and would infer that there's a continuous mass distribution that stars and brown dwarfs just form alike, but in reality, the brown dwarfs are a separate mass function, which is given by this power law here, and then it stops, and then there's the stellar mass function, which is separate from that of brown dwarfs, and then together then gives this red curve. And so we did this for all these systems, and you can see that the model always agrees very nicely with the data as long as one treats the brown dwarfs as a separate power law mass function. And one finds that the mass function of brown dwarfs is always quite similar. It has a slope of about 0.3, but it's discontinuous. It's separate to that of stars. Okay, and so we've uncovered a fairly important result concerning star formation. These calculations also tell us, given the data, that 1 brown dwarf forms per 5 stars, which is consistent with the previous surveys I've mentioned at the beginning of the talk. And so brown dwarfs are common, but they have their separate distributions. This number takes into account that stars form as binaries, which are dynamically processed. And this is now important to realize that if an observer sees a system which is dynamically not processed, so 100 systems correspond to 200 stars, one would see 40 brown dwarfs per 100 systems in such a star cluster. If this, remember that, however, brown stars, the binaries are broken up, so this here actually increases, because in total we have 200 stars. So if the binary fraction is 0.5 and the observer sees 100 systems, there are in fact 150 stars in there, but the observer would deduce that there are 30 brown dwarfs per 100 systems just from observations. And if there were no binaries, the observer might deduce that there would be 20 brown dwarfs per 100 systems, although fundamentally it's always the same type of object, the same number of brown dwarfs, the same number of stars. It's just as the stellar population, the binaries are broken up through the dynamical encounters, the observer will deduce a variation of the number of brown dwarfs per star, because that star is either unresolved system, binary system, or not, and has been broken up or not. And so this is very important to realize. And so the binary fraction is a function of mass of primary. I will be ending very soon now. So we know that angular momentum conservation of the forming, collapsing prestellar core implies that most, basically the hypothesis is quite reasonable, that all stars form as binaries. Then these triples and quadruples decay in a very short time, but we observe that a large fraction of stars are in binaries at 1 million years, and so old young stars in low density embedded clusters are binary stars. So this is what we observe, and therefore we can't form triples and quadruples in large numbers. So most stars must form as binaries simply because of this argument which I brought up previously, and this is a very important argument to remember. And so what this implies is the following. Here we have the fraction of binaries as a function of primary mass. We start the population with 100% binaries, independent of primary mass. So that's what the star formation gives us here. And the brown dwarfs would be down here. They form only a few binaries. So initially there's a large step. If we look at a very young population which is not dynamically processed, we see all stars in binaries, and then a large step and only a small fraction of brown dwarfs in binaries. But then as dynamical processing occurs, and if we then, and these embedded clusters destroy the binaries, become part of the field, then we would see this distribution. So the model which starts up here evolves through dynamical processing to these curves, depending on which initial radii these clusters have. And these are the observational data. So the observer in the galactic field, as well as in clusters in which have processed the binary population, finds that primaries which are more massive have more companions, have a higher binary fraction. So for example, F-type stars have about a binary fraction of 70%, while G-type stars has a binary fraction of about 55%, and M-type stars, so M dwarfs, have a lower binary fraction of about 40 or so percent. So the community says that the binary fraction decreases with primary mass, and that's what star formation gives us, and that's wrong. What star formation gives us is that all stars, or very large fraction of the stars, form as binaries, and it's the dynamical processing in the embedded clusters which then gives this trend. Yeah, and the brown dwarfs would be in this regime here. It's a very important point, and it's always done wrong in the community today, who think that this is what star formation gives us. That is not correct. Okay, so so these are typically old systems, and young would be up here. And so the origin and nature of brown dwarfs, that's the final part. We use, so we now know that brown dwarfs don't form in molecular clouds like stars from collapsing molecular cloud cores. But then how do the brown dwarfs form? So we use the Dragon SPH code. These are simulations which Ingo Thies has done to study the effects of stellar encounters in embedded clusters on external regions of early circumstellar disks. So we take a star, put a circumstellar disk around it with radiative energy transport, a cooling function, and so on, and allow a second star to pass nearby, thinking that these are in an embedded cluster. So these encounters are indeed quite common in these embedded clusters. And this is what happens. So this is now the movie. You see, this is the scale of 100 AU. This is our star. And you see the disk is rotating. And then a second star comes into this regime. So this is a fairly tight encounter with something like a few hundred AU, which is which happens in these embedded clusters. The second star takes material from this disk and forms a new accretion disk around it, while this star here is so perturbed that it now breaks its disk up into individual components, which are all brown dwarf mass. And then the system keeps on evolving. You can see matter falls onto the star, some of these clumps also, but they interact. At some point, you see they actually form multiple systems, like just now they paired up, then they unpair again. And you see that they have their own accretion disks. They're accreting from the circumstellar material. It's wobbling because the movie is centered on the center of mass of this system. And all of these accrete and become stars ultimately. Just one of them, just a second, one of them is ejected, and that ends up as a brown dwarf. This one here is ejected, and it takes with it so little mass that it cannot accrete and becomes a brown dwarf outside of the star. And this is essentially the origin of the brown dwarf population. So we've done many of these simulations. We can see that we can nicely follow the dynamics. We can calculate how many of them pair up. It's about 15% surprise. And so we find the mass distribution of these brown dwarfs which form in these circumstellar disks which are perturbed in embedded clusters. So that's the number versus mass. You see, this is the brown dwarf regime here. And this slope, surprise, surprise, happens to be very comparable to what we actually inferred by treating the brown dwarfs as separate populations from the star counts. And so there's an incredible consistency between theory and observations. And the brown dwarf function mass function is separate from that of stars and has a shallow slope of 0.1 with a fairly large uncertainty of 0.3 or so. And so if this is the correct description, then observations of the multiplicity fraction in Taurus Auriga and similar low density star forming regions allow a test, which we've quantified. So there are predictions for binary fraction independence of primary mass, because we can now test this theory for the origin of brown dwarfs. And that's done here. So we have here the binary fraction is a function of the primary mass in the Pleiades, which is 130 million years old. This is the prediction of the model. These are the observational data in the galactic field. And this is what we should get in the Pleiades, this line here, and the brown dwarf should be here. Then we did this for the trapezium cluster. You see it's comparable. And then we did this for the IC348, and then for Taurus Auriga. Taurus Auriga are very low mass little embedded clusters which have not dynamically processed the population, only a little bit. So this is the initial distribution function up here, and that evolves in Taurus Auriga to this at 1 million years. And so in Taurus Auriga, we expect nearly all stars to be in binaries. Well, that's something we already know. And then to be a strong drop in the brown dwarf binaries to be very at the 15% level. That's what the theory expects. This can be verified by observation or falsified. And this is this research paper using binary statistics in Taurus Auriga to distinguish between brown dwarf formation processes by Michael Marx et al. And so I'm ending here at the conclusions, just as a summary, the distribution of masses and the pairing rules of stars are well understood and simple actually. So the birth binary population, or we can call that the standard model, which is defined by these 4 distribution functions, initial distribution functions. There exist unified rules or laws which do not distinguish between an M dwarf and a G dwarf, for example. Brown dwarfs cannot be added into this birth binary population without violating all binary star observables. Brown dwarfs can only be added into this birth binary population with additional rules which apply to brown dwarfs separately. And these rules, so IMF of brown dwarfs, binary properties of the brown dwarfs, come out to be consistent with the theory of brown dwarfs forming in gravitationally pre-processed material, so in the external regions of protostellar disk. So essentially, you cannot form a brown dwarf directly from a molecular cloud, but you can form brown dwarfs from a circumstellar disk in the outer region where it is induced through an encounter for perturbation to collapse locally, and the material is limited because the circumstellar disk has only a certain thickness and a certain amount of material in the vicinity of this collapsing structure. And so that's what gives the majority of brown dwarfs out there. So many very low mass stars form brown dwarf-like. At the intermediate regime, there are stars which form like brown dwarfs. And there are also some brown dwarfs which do form like stars directly from the collapse, but they are quite rare, so they do overlap. If we compare this to planets, we know that planets also have their own distribution rules. They form with stars, but the planets are not an extension of the stellar IMF into the planetary regime. And so this is where I wanted to end. Basically, I would maybe like to just conclude by saying that the fact that we observe many brown dwarfs out there is just another statement of the fact that that stars form in embedded clusters with small radii where star-star encounters are common. So brown dwarfs are accidents from the stellar encounters in embedded clusters, which are the same encounters which shape the birth binary population into what we see in the galactic field. So thank you, and yeah, I hope I'm not too much over time. So thank you for listening.
And we thank you very much for your talk. Now we have some time for questions. So please, in any way.
May I have a question, Pavel? There is Michal Křížek.
Hello, how are you?
In our neighborhood, are there more red dwarfs or brown dwarfs in a close neighborhood of the sun?
There are still more M dwarfs. So we have about what were the numbers? About 10 for 10 stars. We have about 2 brown dwarfs roughly.
Okay, thank you, thank you.
I think there is a question by Frantadinbir. So please.
Hello, Pavel. Thank
Hello.
you very much for this interesting talk. I would like to ask you about the threshold for these 2 different ways of object formation, as I understood it.
Yeah.
That brown dwarfs are likely formed in the disks because they are not likely to be formed by the large-scale fragmentation of clouds.
Mm-hmm.
But this threshold of 0.08 solar mass for brown dwarfs
Mm-hmm.
is something which is given later. Like if an object forms and it has mass 0.05 solar mass or 0.1 solar mass, the object does not a priori know whether it will end up as a brown dwarf or as a lower mass star, because it takes roughly 100 megayears before the hydrogen burning starts at its center. So it seems to me that this threshold is just a coincidence of something else.
Yeah.
And is there some theory or some estimate what this mechanism which distinguishes between these 2 different modi of object formation, which it is?
No, that's a very important point you're raising, and it's true. So one cannot say that stars, so objects which are above 0.08 solar masses, form in one way, and stars which are objects which are below that form in a completely different way. That's not correct. Nature doesn't do that because, as you were correctly saying, when the collapse begins, it doesn't know what it will end up as. So what we've uncovered is that there are 3 populations. There are the planets, there are the brown dwarfs, and the stars, but there are overlaps, right? So the planets go up to objects which are Jupiter mass or even more massive, and they are indistinguishable from their properties or nearly indistinguishable from brown dwarfs, in the sense that Jupiter probably formed with first pebble accretion and then accretion of the rest of the atmosphere, or through direct gravitational collapse. That's basically the question. So the idea is that planets form from accretion of coagulation of pebbles, which then accrete gas. A brown dwarf forms like a star, just a gravitational collapse of gas. however, not directly from a molecular cloud, and stars form from direct gravitationally collapse. That's the broad picture, but in the details, we can see this from this a plot here, where this is the mass function of brown dwarfs, or actually more correct, this is the mass function of objects which form in the disk, and you can see we form stars. So there's no distinction in that sense that there are very low mass stars which form like these brown dwarfs in the circumstellar disks, and they of course overlap in this regime to provide part of the stellar population, while a molecular cloud also makes through direct collapse some brown dwarfs. So it's not like there's a strong cutoff, but some brown dwarfs at a mass, say, in this regime can form from direct collapse, but they just become rarer and rarer because the direct collapse is more and more difficult as we go to lower and lower masses. And so basically, as we go here from direct collapse into the regime where there's an overlap, where both type of populations contribute, and then we go more and more into the regime where at these lower masses only the objects contribute which formed in the circumstellar disk, simply because they simply can't form from direct collapse in a molecular cloud, but they can form from direct collapse in a circumstellar disk. So there's no real hard cutoff. It's an overlap of populations, just like if you look at brown dwarfs, there's probably an overlap with a planetary population too.
Thank you.
Then we have a question in T1.
Do you hear me?
Very poorly, please. Could you?
I will try once again. So it's probably closely related to the question of František, right? Because it seems to me that you would need some strong mechanism which would prevent a direct formation of brown dwarfs from a giant molecular cloud, from a direct collapse. Right? What kind of mechanism would it be?
Well, there's no mechanism which prevents it. It's just a question of likelihood. The conditions which make which would be able to make a brown dwarf are extremely rare, because you have to imagine that you need a little molecular cloud core, that overdensity molecular cloud, which would collapse to make a brown dwarf. It has to have a mass which is below 0.08 solar masses. So it has to be very dense to be able to collapse under self-gravity, and it must not have surrounding material which would accrete onto it, so that it would end up again more massive than the 0.08 solar masses. And the combination of these requirements just makes it simply very unlikely. That's it. So it's not like there's a mechanism which doesn't allow brown dwarfs to form in molecular clouds. It's just becoming unlikely. It's just like massive stars. If you look at the high mass end, the formation of very massive stars is extremely unlikely. You need very special conditions to make these very massive stars, and that's you simply need a very massive molecular proto cluster cloud core, so that the densities in the inner region, which would make these stars, are so the density is so high that they start merging and merge very quickly, and there's a lot of accretion to make these massive stars. So you need very special conditions to make these massive stars. You need very special conditions just in a molecular cloud to make brown dwarfs, and both ends are very, very unlikely. However, since stars form from accreting material, the conditions in the circumstellar disks, or in the accretion disks, they again are favorable to formation of brown dwarfs. And so that's how this brown dwarf population appears. Yeah, is that relatively clear, or is there still something which might not be so?
Mira is happy.
Okay, good. Thank you.
Then there is a question of Zhiqiang Yang.
Hello, Zhiqiang.
Hello, Pavel. Yeah, you mentioned that the pairing rule for the binaries of star more massive than 5 solar mass is different than lower mass stars. Can you elaborate?
Well, what we see from observations, you see that there's no theoretical statement on this whatsoever. I mean, there doesn't exist a theory which actually tells us what the distribution functions are. I mean, we don't really have a theory for the IMF. We don't have if you don't even have a really good functioning theory for the IMF, we of course have no theory for how these stars would actually make an initial distribution of binaries, right? But from observations, what we find is that so we can start with the hypothesis that we make the massive stars follow the same pairing rules as these low mass stars. So we take a massive star like 100 solar mass and just randomly take a star from the IMF and make a companion. And then we can compare this type of population with the observations, the star counts, where we can see massive stars and actually look at the companions they have. And this is in total disagreement. I mean, what we find is that about a 5 solar mass, I mean, this could be 2 solar masses or different, this is not exactly known, but above that, we need to invent new rules. So we find that when we make a massive star, and we know that most of these massive stars, when they are born, are in binaries. They might even be in triples or quadruples, but we then have to take companions which are also massive. So we have to restrict choosing from the IMF only to the massive regime. Yeah, and how the mass ratio distribution actually looks like we don't fully know. At the moment, it looks like we just make a cut at 5 solar masses. These ones are then treated with random pairing among each other, and the ones below that are treated with random pairing among each other. And so this we know works exceedingly well given the data. But up here, this is still being investigated. So Franta Dinbier is actually working on this and very interested in trying to understand the pairing rules for massive stars. So the idea is that we need to infer a mathematical model when we want to initialize a stellar population which contains massive stars and then take into account that they are in binaries, maybe triples or quadruples. We need to know the distribution functions, how to do that. And this is something which we are now addressing, and Franta is keen on doing this, and he's actually working on this at the moment. So I think there's a lot to be discovered here, but we understand the binary population below a few solar masses, below something like 5 solar masses, and we understand the brown dwarfs now, I think also rather well. But what we do not know yet is whether this ratio between the brown dwarfs and low mass stars, which we see in the galactic field, so galactic field and nearby star forming regions, which means 10 stars gives us about 2 brown dwarfs. Does that ratio also apply in globular clusters? That is something which is completely unknown. Intuitively, I would think that it cannot, because when globular clusters form, they're formed like extremely massive, very, very luminous systems, probably with a top-heavy IMF, such that low mass stars should not even be able to form because they would be photo evaporated away. So it's quite possible that in globular clusters we might have a significant lack of brown dwarfs. But this is something to be yet looked at. And Andrea Dibal here has HST programs to try to find brown dwarfs in globular clusters. Imagine they're 10 billion years old, so they're exceedingly faint. And maybe the JWST will be able to give us constraints on that.
Thank you.
Any other question? I don't see anything. So if that is indeed the case, then I will thank Pavel again for his nice talk. And I will thank the audience for coming and taking part in the discussion. And I will be looking forward to seeing you next week. Goodbye.
Bye-bye. Thank you.
Bye.